Good morning everyone, or good evening or good afternoon, depending on the time zones where you are. Welcome to our WaterTOP meeting. It's a pleasure to host you here in Porto. So let's start with our first hybrid presentation. And I will give the word now to the chair of this session, Marta Barbosa. So Marta, please, thank you.
Good morning, everyone. It is my pleasure to introduce Dr. Vera Homem from LEPAB, hosted by Faculty of Engineering of University of Porto, who will give us a talk about synthetic fluencies in aquatic environments, the sense of danger. Vera is assistant researcher in the research group of environmental science and technologies at LEPAB. She has a PhD in environmental engineering, and her major research topics include the development of analytical methods of detection of emerging contaminants, environmental monitoring of trace pollutants, environmental risk assessment, development of chemical scoring and prioritization systems, and also remediation technologies. Before giving the word to Vera, I would like to ask the participants to feel free to raise their hands and for any questions and discussion. So at the end, we can have a fruitful discussion. Now, Vera, the floor is yours.
Thank you, Marta. I think everyone is hearing me, yes?
Yes.
Okay. So, good morning. As Marta said, my name is Vera Homem, and I'm assistant researcher at LEPAB. First of all, I would like to thank Dr. Rita Ribeiro for inviting me to be present in this meeting and for having the opportunity to present some of the research work that we have been developing in our group. Today, I'm going to talk about the presence of fragrances in aquatic environments and their potential risks. I will divide this presentation into these four main parts. First, I will make a brief presentation of the research group where I work. Then I will make an introduction to the theme of fragrances, mentioning their historical evolution, use, market and legislation, relevant properties and fate in the environment. Afterwards, I will present some important issues about the analysis of these compounds. And finally, I will present two case studies focused on the analysis of fragrances in aqueous matrices. As Marta said, I'm working as assistant researcher in the Environmental Science and Technologies group at LEPAB. More specifically, our laboratory is dedicated to environmental and trace analysis. And in the last years, my research work has been focused on development of new analytical methodologies, trying to use green approaches for the determination of emerging contaminants, usually at trace levels, the monitoring, environmental risk assessment and prioritization systems. And I also have worked with remediation technologies, namely advanced oxidation process. To give you an idea of the work we have been developing, I present on this slide the four projects that we have in progress and in which I am involved. The Agronaut project, which intends to contribute to improve the knowledge on the safety use of sewage sludge on cropland, with a special focus on the presence of emerging contaminants, synthetic musks, which is a type of fragrance, and also volatile methyl siloxanes. The Lancelot project, which has as main goal to study the presence of siloxanes in wastewater treatment plants and to propose new solutions for their removal. the Cytostratec project dedicated to development of cost-effective treatment solutions to prevent the entrance and the accumulation of cytostatics, the drugs used in chemotherapy, in the water cycle. And finally, the SafeCall, which is studying the safety use of rubber crumb from recycled tires into the synthetic turf pitches. Moving now to the theme of this presentation, the fragrances. They can be defined as organic compounds with pleasant odors that may be incorporated in different products to impart a specific aroma or to mask unpleasant odors from raw materials. Fragrances are incorporated in different products of our daily life, such as perfumes, cosmetics, and household products. Fragrance substance may have natural or synthetic origin, and in theory, they should be stable, non-allergenic, and easy to manipulate. Here you can see some examples of types of fragrances. For example, the essential oils, the synthetic musks, terpenes, estates, etc. In fact, we can say that the origin of fragrance industry lies in the prehistory. By the time that writing development, there are some references to the use of herbs and also spices as voting offerings to the gods and supernatural world. In the classical period of ancient Greece and Rome, the use of different oils, spices, and perfumes is also described. It was in this period that some important techniques in the perfumery were developed, as the concept of the extraction and also development of the distillation techniques. During the medieval era, the powerful church disapproved the use of fragrances, claiming that their use was a vanity. So only between the 15th and 18th century, the classical science was rediscovered and the modern chemistry was developed, and an important milestone in the fragrance area was the development of the thermometer. The industrial age marked the beginning of the fragrance industry as we know it, with a special emphasis on the creation of new analytical techniques essential for the identification and purification of substances. In fact, nowadays, the fragrance market is valued at around 2 billion euros. These ingredients are mainly incorporated, as I said, in cosmetic and personal care products, and Europe is the biggest consumer of this type of ingredients. Regarding regulation, in fact, this is very scarce. The fragrance industry has established self-regulation involving the two main international fragrance organizations, the International Fragrance Association, IFRA, and the Research Institute for Fragrance Materials. The European Chemical Agency, ECHA, through the REACH regulation, also defines some guidelines. Fragrance ingredients in cosmetic must meet same requirements for safety as other cosmetic ingredients according to this regulation, in which fragrances are, of course, included. In fact, there are fragrances with very different chemical structures, as you can see here in this slide. And consequently, different physical-chemical properties. However, they are all volatile or semi-volatile compounds. They are usually not readily degradable and present some potential to bioaccumulate. Considering the broad spectrum of chemical structures, also a very broad variability of ecotoxicological effects is also expected. Some of these fragrances may cause allergic reactions or are associated to the prevalence of asthma and other respiratory problems, may act as endocrine disruptors, and are toxic, for example, to the aquatic organisms. So it is essential to study their presence in the environment. As mentioned before, fragrances are used in a widespread range of daily life products. After their use, residues of fragrances are discharged down the drain to the sewage system, reaching the wastewater treatment plants. Unfortunately, most of them are not totally removed during these treatments, being discharged with the final effluents to the environment, reaching several compartments. In fact, fragrances have already been detected at concentrations up to hundreds of micrograms per liter in different water samples. As everyone knows, in quantitative analysis, sample preparation can be one of the most complex and time-consuming tasks, especially when compounds are present at trace or ultra-trace levels. So the new techniques for sample preparation combine the principles of green analytical chemistry and the simplicity, low cost, short time, and high efficiency of extraction. In fact, the miniaturization is the current trend with the elimination of the use of large amount of organic solvents. And this also happens in the analysis of fragrances in the environment. Solid phase microextraction and dispersive liquid-to-liquid microextraction are two examples of these kind of methodologies. However, before moving on to the case studies, it is essential to mention some important issues when analyzing fragrances. In fact, the development of protocols that minimize the possibility of external cross-contamination due to the potential presence of fragrances in the field and lab environment is mandatory. Researchers should avoid using perfumed personal care products, and household products should not be used in the labs. The extraction protocols should minimize the sample and extract handling and preferably be performed in closed containers. Sample handling and the extraction procedures should be performed inside clean chambers or clean air cabinets with appropriate air filtration to minimize background contamination. And of course, it is essential to perform field and lab blanks to control those potential external contaminations. Now I will present you some results of our research group about the development of an analytical method based on ultrasound-assisted dispersive liquid-to-liquid microextraction, followed by GCMS analysis to quantify several synthetic musk fragrances in water matrices. These kind of fragrances are semi-volatile, and have lipophilic characteristics. In literature, the traditional liquid-liquid extraction and solid phase extraction are the most common extraction techniques to analyze this type of compounds. However, as we know, they are time-consuming and use relatively high amount of organic solvents. So we decided to develop a dispersive liquid-to-liquid microextraction procedure. And here you can see a simplified diagram of the adopted protocol. We use acetonitrile as dispersive solvent and a few microliters of chloroform as extraction solvent. The formation of the cloud solution was promoted by ultrasound agitation. This methodology was tested using different types of waters, tap water, river water, seawater, and wastewater, influent and effluent, and the extraction conditions were optimized using design of experiment approach. Those were the factors investigated, and these are the optimal extraction conditions found. Here we can see an example of a response surface plot obtained for the musk tonalide, and the bluish green zone corresponds to the optimal conditions that we set here. The analyses were performed using the GC-MES ion trap system. This methodology resulted in low detection limits, nanogram per liter, a good precision, and as you can see here, also a good accuracy. The applicability of the method was tested in those different aqueous matrices, and higher levels of synthetic musks, as expected, were detected in wastewater matrices, namely in influent. And the musk galaxolide and tonalide were the predominant compounds. Using this methodology, we performed a monitoring study in a Portuguese wastewater treatment plant, collecting influent and effluent samples. They were 24-hour composite samples that were collected during the summer and also winter. Synthetic musks, as you can see here, those levels were not seem to vary significantly with the season, and galaxolide is the predominant compound. As previously mentioned, these compounds were not totally removed from the waterline during the treatments. So, an environmental risk assessment study was also performed, considering the worst case scenario using the maximum concentrations found for each compound in the treated effluent. We followed the methodology used by the European Union and calculated the predicted concentrations in the surface water and compared those values with the non-effect concentrations published by ECHA. In this specific case, hazard quotients were always below 1, indicating non-potential risk due to the presence of these compounds. Then we decided to perform some monitoring studies in river waters to verify if the predicted concentrations were far from those measured. We decided to study different personal care products, in which we included 7 synthetic musks and 15 other fragrance, in this case, fragrance allergens. And we developed a new methodology based on solid phase microextraction in collaboration with our colleagues from Santiago de Compostela. Once more, the extraction conditions were optimized using design of experiments. And here you can see a simplified diagram of the procedure. For this work, a GC-MES triple quadrupole was used, and you can see here the main extraction conditions. Once more, this methodology resulted in low detection limits, nanograms per liter, with a good precision, usually relative standard deviations below 10%, and a good accuracy, as you may see here. Then we use this methodology to monitor 4 Portuguese rivers during summer and winter, collecting samples from spring to the river mouth, and we detected around 16 fragrances in those rivers. These 4 compounds and also galaxolide were detected at higher concentrations. We also performed an environmental risk assessment study similar to the one described before, And we concluded that at some sampling points, especially after wastewater treatment plants discharge, hazard quotients were greater than 1 for 2 compounds, geraniol and the musk tonalide, which may indicate presence of environmental risk. So this should be studied in more detail in a near future. So to conclude, although it is a difficult work and sometimes also time-consuming, it is essential that we continue to develop new methods for trace analysis of emerging compounds, such as fragrances, in the different environmental matrices, and trying to use green chemistry approaches. These methods should be simple, fast, and relatively inexpensive so that they are easily implemented in monitoring protocols in the near future. So, thank you very much for your attention.
Vera, thank you very much for your great presentation. I will try to give the word to the participants in the same order they raise their hands. So feel free. Okay. Despo, please. I don't know. Okay.
Yeah, hello. Actually, it was my hands clapping for congratulations. It was a very nice talk. Thank you very much. But since you gave me the floor, I have a small question. When you look for the impact of these compounds, do you look them individually or, the sum of them?
Individually.
Individually.
Yes. In this approach, we try to do it individually, and now we are trying to do some environmental risk assessment using new models that are trying to use the synergetic or antagonism behavior of these compounds. But for now, we are seeing them individually.
But you see a reason why we should probably look for additional or synergistic effects. Yeah.
It is possible. Sometimes we see described that for some ecotoxicological studies that, for example, the synthetic musks, I have been studying for a long time this type of compounds. The presence of tonalide with galaxolide, for example, in a mixture may have higher toxicity than each of them individually. So
yeah.
In the near future, we need to have some protocols, some type of methodologies that take into consideration the presence of these compounds at the same time.
Yeah. Thank you. Thank you.
Thank you very much.
Nice work. Thanks.
More questions? Please.
Martin Steinhaus, in your talk you mentioned the importance of blanks, which I want to totally support. Can you explain the difference between what you mean with lab blanks and field blanks, please?
I'm sorry, I'm not hearing very well. Martin, maybe you can...
Oh.
I'm so sorry.
Sorry.
So my question refers to you're mentioning that blanks are so important, which I totally support. It's also my experience, and it's sometimes difficult to explain to people in practice. But can you explain what you mean with the difference between lab blanks and field blanks?
Yes. For example, we also study the presence of this kind of compounds in, for example, in air compartments. So when we do this kind of analysis, we took samples, for example, for the environment, for the labs blanks. We performed those analyses of blanks in the lab with the old protocol, but we also sometimes perform some analysis of for instance, for air collected in near the sites that we perform the sampling. So we compare those, and of course we do the extraction protocol. Then we do the comparison between the results from the lab and also the results from near the points that we do our sampling. For example, we do it with different matrices, but for air, for example, we do like this. I don't know if it was what you are looking for in that question.
Yeah, thank you.
Thank you very much.
We have one more question from Zuhal Zenni. Is there any customer complaint or report from tap water for those compounds you analyzed before?
For tap water, okay. I saw, I think 3 or 4 years ago, a study that included the presence of synthetic musks in a drinking water facility. They tested the presence of these compounds, but they have a problem with analysis regarding the limits of quantification and limits of detection. Of course, the presence of this kind of compounds in tap water are expected to be low, and the methods that were applied to the detection of these compounds present relatively high limits of detection. So this kind of protocols are very, very difficult when we are applying to tap water or and even, for example, for seawater, and we have there are matrices that we are expecting great dilution factors. So at the time in our group, we are trying to develop some methods that are that have limits of detection small enough to do this kind of protocols. But usually to achieve those low factors, we usually need to use great volumes of samples, and sometimes they are not available to do those kind of extractions. And also we think about the use of green approaches, the use of low quantities of solvents, and this is in fact a problem. So I think that the presence of this kind of fragrance must be, in fact, they must be present in small levels, but for now we don't have any information about the toxicity or it is a danger for the tap water.
Thank you, Vera. One more question from Dr. Trika Ludis. What kind of design of experiments you used for VLLNA optimization? Which factors were optimized?
Okay, let me see here, because it was performed from just a second. Okay, the factors that we have optimized were the type of extraction in dispersive solvent, also the volume of those solvents, sample volume, the extraction time, and the use of a salt. So the ionic strength was also tested. And we performed this extraction this optimization of this extraction in two parts. In a first part, we do the optimization of the discrete variables, and then we do a CCD protocol to perform this optimization.
Thank you, Vera. Two questions in the room. So the first one, please.
Thank you for your presentation. I want to ask, from all your findings, do you think that there are compounds that can be used as markers of pollution in various water matrices?
Vera.
Which compounds? I heard the first part of the question, but then I didn't heard very well.
Compounds, can we use it as
markers?
As markers?
In the various water matrices.
Okay, in the
markers of pollution.
In the various water matrices. Like indicators.
The fragrances?
Which compounds? Yes.
Okay, yes. For the analysis of fragrances, I think that thinking about those compounds that have low volatility, we should use, for example, galaxolide as a marker. It is the compound that is present in most personal care products. They are also galaxolide. It is also used in household products. So I think it would be a great marker. In fact, the presence of galaxolide has been studied all along these recent years, exactly as a marker for this subclass of fragrances. Sometimes some authors also used more volatile compounds as geraniol or eugenol as markers for the more volatile compounds in environmental compartments, but they are usually used more in the monitoring of air, not in water, because they are more volatile. So these are the types of compounds that usually are used as markers.
Thank you. Question more? Yes, thank you. It's easier.
Thank you for your presentation. It was very interesting. I'm Maura Manganelli from Italy. I kind of new in this area of compounds, so maybe these fragrances are very well known, but I was wondering if there is the odor threshold concentration for all of these compounds. Maybe for some of them is available the OTC, or maybe not, because this could give us some information about the risk for tap water. So if we have the odor threshold concentration, and if these fragrances are used also as food fragrances, probably there is already a risk assessment from EFSA or from other EPA, from other agencies. So knowing the OTC and if they are used as food fragrances, we could have an idea if the concentration that you can detect can be a risk or not for tap water. Thank you.
Yes, thank you. In fact, some of those fragrances are also used in as food additives. Yes, they are used. And we have some information about the thresholds of some of them, not all, but some of them are available. We can see it from the European Chemical Agency. They have several environmental risk assessment studies, but the toxicity levels, thinking about the aquatic environment, that is the compartment that has been mostly studied within the environmental compartment, we can see that in the recent years, the levels of toxicity for some species have been lowering, and so the European Union also has some doubts about the toxicity, the real toxicity of this kind of compounds. So, but yes, there are some information that can be seen in literature, yes.
Thank you, Vera. More questions? No? So thank you very much for all your interventions. Thank you, Vera, one more time.
Thank you very much.
Before closing the session, I would like to remind everyone who is not here with us that at 2:30 local hour in Portugal, we will have a presentation from Dr. Martin about key elements in foods, identification and use for targeted product improvement. We look forward to meeting you again. Thank you.